I wish to thank Joel and Avishai and the other organizers for having me here. This is one of my favorite series of workshops. This one. So let me jump straight into the talk, which actually ties back to the first talk of today by Joanna, and I will say some of the things that she already talked about, but in a different way, as you will see. So we are very aware of this series of bimodalities that observed at any redshifts, right? So blue galaxies, star-forming galaxies, the blue cloud galaxies are star-forming galaxies. The red sequence galaxies we associate with quenched galaxies. Star-forming galaxies look like disks and behave like disks, have high V over sigma properties. The quenched ones are spheroidal looking, at least, or if you can analyze their morphology in details, they are spheroids of various shapes and properties and are characterized by a low rotation fraction. And if you can look at high redshifts, the information is limited. We typically model galaxies with simple tools like the Sursich profiles. And if you plot in the UVJ diagram, classical diagnostics for star formation and passivity, galaxies and color code their morphology characterized by their Sursich index, you do see this bimodality. High Sursich index are typically associated with spheroids, which are in the quenched regions, low ones with disks in the star-forming sequence, and this is observed pretty much at all redshifts where we have been able to do the measures. This is up to redshift something like 1.5, and this is all the way up to 4 or so, just shy of 4 actually, 3.5. All right, so, but what we want to understand is when this bimodality happens. Is this structural transformation something that happens in proximity with quenching, during quenching maybe, or just around quenching, or is more like a secular transformation? Joanna has discussed some of these transformations today, focusing on the role of dissipative gas accretion to the center, or the lack of. But what we want to understand also is there any evidence of these transformations along secular times, and in particular, how the galaxies lose their angular momentum and come to give rise to early type galaxies as we know them, fast rotators, slow rotators, and so forth. I'll come back to this plot later. So Joanna described this plot today. Still working? Yeah. Let's try a different thing here. And this is the elbow plot that here is shown in this mass bin in particular. This is a lower mass bin, otherwise identical. Sigma 1 is here, the projected stellar density in the 1 kiloparsec radius versus the distance from the main sequence essentially here. Main sequence is between green and blue light. The quenching threshold is this orange one, starburst regions is here. And you see the redshift bins. And color-coded is the age measured with one of our very own algorithm, but actually it agrees very well with other algorithms around. This is from a recent paper by Bomili. But there are other measures, and we generally agree with those measures. As you can see, the elbow diagram that Joanna showed is observed with larger dispersions in a smaller mass bin, but essentially when they form stars, galaxies span a fairly wide range of central density. By the time they're quenched, this dynamic range is much restricted and all the way up to the top value. There are blue nuggets and there are red nuggets, but once you're quenched, there are no blue nuggets anymore. They're just red nuggets, and there is no nuggets dead galaxies, or if there are, they're very rare. But, and this is the same diagram, presumably the same data that Joanna showed this today. But if you look at, does this state of affair change with redshifts? The answer is actually no. So this happens in each redshift in the same way, suggesting that this is what happens as galaxies quench as they evolve and then evolve through quenching. But if you plot in different, so this is for three mass bins, redshift is color-coded, for both star-forming and quiescent separately. So this is the evolution of the distribution function. This is the cumulative distribution function of sigma 1. The story repeats itself at all redshifts. There is a little bit a hint of evolution in the small mass bin among quiescent galaxies, which probably is the disappearance of the red nuggets today. They're very rare today. But pretty much, there is no secular evolutions of this state of affair. So how does the transition happen? And what is the nature of the early passive galaxies? So a few years ago, Arian came up with this paper suggesting that recently freshly quenched galaxies are disks. And this evidence was pretty much based by his eye judgment looking at the axial ratios of the galaxies. And even if they didn't show in the paper a distribution function, they only had a few galaxies, a couple dozen, something like that. I forgot the number of the sample you analyzed. But based on their essentially visual evaluation of the axial ratios, here showed some of their samples, they concluded that they are disks. And the paper stirred quite a bit of debate. People said, how do you know that these are really disks? There was no kinematical or dynamical information. A few years elapsed, and thanks to the help of powerful clusters that lens background passive galaxies, now we do have some result kinematics, although overall the information remains scant. This is by a recent paper by Andrew Newman. I thought I put the reference in it. But anyway, this is Andrew Newman 2018, a PJ paper, who analyzed, after reconstructing 3 out of the 4 cases, the mass distribution, solving for the lensing models, and found that actually these galaxies do behave like disks. They have a distinct rotation curves. This is the 3 cases for which the mass model could be reconstructed. This is the one for which the mass model could not be reconstructed, but you do see a rotation curve here too. And this is the velocity dispersion profile. So if you put these galaxies in the specific angular momentum at RE versus ellipticity plot, you do see that for a given, and here, this is the boundary between slow and fast rotators proposed by M. Seller a few years back. These grids are grids of constant intrinsic ellipticities and constant inclinations. The high redshift passive galaxies have a lot more angular momentum than either fast rotators or slow rotators. So they really look like disks, essentially vindicating Arian van der Velde's claim based on just Hubble morphology and his very good eye. So if 3, let's say 4 galaxies, assuming also the 4th galaxy behaves like this, are representative of the general population, something that needs to be validated, we don't really know at this stage, then the transformations that produced our dispersions supported early type galaxies did not happen at quenching. So while we wait for ELT and TMT and GMT to be online, can we find other evidence that actually this is the result of secular transformation? Can we find another evidence of secular transformations in galaxy structure? So I propose that Sursic N is not a good diagnostics for that, mostly because galaxies don't really obey one single Sursic profile. And this is the result of a study that my graduate student, Juan G, is conducting. Basically, the bottom line is that N is very covariant, is obnoxiously covariant with RE, which actually remains. So this is plotted as a function of flux, essentially a proxy for signal to noise and surface brightness. Covariance profiles of N and RE, delta RE over RE, delta N over N. The lines is the 30% variations. And in blue, there is the fractional variations of sigma 1. The bottom line is that RE and sigma 1 are well behaved. You can somewhat measure them for various combinations of flux and resolution. But N is very covariant. Plot here is the as a function of signal to noise integrated in the H-band from the candles images, the 1 sigma covariance ellipsoid side, N is the one that does the worst in our analysis. Here is a beautiful example of 1 galaxies only. V-band image is the rest frame UV, mid-UV light. The H-band is the optical B to V light. Same isophotal signal to noise. Covariance between RE and N. The galaxy must have some red nuggets at the center, which sends N crazy, whereas RE remains well-behaved. In the U-band, you don't see the red nuggets at the center. N is much better behaved. The B-band doesn't have very good signal to noise. So I propose something else. We use some other metrics. Which metric we propose? I propose to use a non-parametric matrix, 2 of them in fact, but I'll focus on 1, Gini and M20. Gini, M20 is the second moment of the 20% brightest pixels. I get rid of it with that. Gini is a little bit more complicated. It's the average of fractional, projected matter density or light over in unit of the average one, okay? But I propose to use them not as people typically use them. You know, they measure Gini and they say, okay, a disk is supposed to have that, this, a spheroid is supposed to have that, let's see what they do. No. Gini and especially Gini, but also M20 are very noisy. You add a little bit of a lump, they go crazy. So let's not use the absolute values of Gini and M20. They're noisy and difficult to calibrate, and there are a number of papers documenting this several years back here. I listed them here. I propose that differential variations, evolution, are more informative about what goes on. And I also propose to use Gini and M20 in the Petrosian radius. Why the Petrosian radius? You need signal to noise to be able to measure it, which restricts the sample to the cases where the measure can be done. But not only is largely insensitive to surface brightness bias, it is essentially a metric size of the galaxies, but it's also large enough that presumably it also involves volumes of the galaxies with the dark matter also matters in the dynamics of the galaxies. Sigma 1, for example, is too local. In these baryon-dominated systems like massive galaxies, high redshift, there is no appreciable contribution to the gravity by dark matter in those regions. As an example, let me show you the distribution of the effective radii of the sample we adopted. This is 1 kiloparsec. And the distribution of the Petrosian radii. As you can see, we are a factor of, what is it? This is 2, 3. The peak here is about 5. Factor of 5 larger in volumes, 5 to the cube larger volumes. Also, differential evolution of Gini. Forget the right side of this plot. Look at the left one. This is the expected Gini for a given surface profile. Here is N, is RE, right? Fix a profile, you fix Gini. What we're going to look is gradients in this plot, right? Not the absolute values, which you add a little bit of a disturbance, the number changes. So essentially, this is, for example, if you have a situation in which you have a given bulge to total ratio, this is the RE of the bulge versus the RE of the disk, the flux of the bulge over the flux of the disk, Gini changes. What we're going to do, we want to see, where is the direction of Gini, the variations, as this ratio, for example, changes. But what is also the physical meaning of Gini and of its evolution? So I try to derive this. So this is the formal definition of Gini, okay, for any statistical variable x. Now x becomes your mass element. So divide the galaxy in some n number of volume elements. The mass is rho dV. Let's assume that the candle's H-band light is a very good proxy of the mass distribution. We do our mass to light ratio well with the SED fitting and so forth. For a continuous distribution function, this is Gini. You do a little bit of algebra, and you find out that Gini is essentially the volume average over the volume you're considering of absolute density differences in unit of the mass density. Apply the Poisson equation, decompose in spherical harmonics, and do the average. Essentially, is the fractional variations of the potential, of the gravitational potential. The absolute values of Gini, okay? We're not going to measure that. We're going to be differences of Gini. So here is what we observe. If you measure Gini statistically, and also M20, but let's focus on Gini first. There is a continuous, namely secular. I call it secular because it happens at all redshifts with redshifts, not just through quenching. In 3 mass bins, big, medium, small, 3 redshifts bin for both star-forming and quiescent galaxies, you do see that the distribution function of Gini changes. In particular, going from high redshifts to low redshifts, Gini increases. Now, if you recall the distribution, if you recall this plot, increasing Gini thank you means I'm going to the region of spheroids. I'm spheroid, I am early type galaxizing my galaxies, okay? Just from the morphological point of view, I have no kinematical information. This is M20. It follows the same trend, okay? You can do the elbow diagram. You do see, with a lot more scatter in both mass bins, the same behavior. So something at quenching also happens. Remember, you develop in the central part. That is changing Gini also. But this, differently from what we saw for sigma 1 from me and Joanna, this happens at all redshifts, okay? Now, you might ask yourself, can be this driven by the growth of the nuggets? Actually, I don't think so. Plotted here is the evolution of Gini for star-forming galaxies in 3 mass bins, of galaxies with high central density and low central density. M1 is the mass within 1 kiloparsec. It's the same as sigma 1 because, you know, a radius of 1 kiloparsec, the volume within 1 kiloparsec radius is fixed. It's a constant. And as you can see, the same trend happens for the very blue nugget, for the very dense nuggets, and for less dense nuggets. Another question is, this behavior happens for both quiescent and not quiescent galaxies. A very good question that actually was raised to me for the first time by Sandro is, can be the observed growth of Gini in the quiescent galaxies be driven by the always quenching star-forming ones, right? And the answer is probably very likely no. Plotted here with much diminished statistics, obviously, is at any redshift, we simply retain those galaxies whose mean stellar age is older than redshift 3 in particular. And the same evolution is observed. Essentially, as we go lower and lower in redshifts, we prune the galaxies that have quenched recently. So it's still observed. So it's real. Now, I've been given a warning of 5 minutes, so I just want to say this. I think this analysis has unveiled secular large-scale structural transformations. It's only morphology, it's no kinematics, but it's large, on large scales. And it goes in the directions, essentially, of change of what you would expect when a disk, something that looks like a disk, goes into something that looks like a spheroid, okay? What seems interesting to me is that this seems to continue after quenching. It happens even before quenching. The star-forming galaxies do have it very nicely. But it continues also after quenching. So if you think that during the star-forming phase is driven by dissipative gas accretion, which very likely that is a contribution, I think, well, after the quenching is not. So it must be reflecting some other component evolution, presumably the non-dissipative one, stars and dark matter. I'm not going to talk about the timescales. Now, we went to illustrious TMG 100 to see whether this also happens in the simulations, 1 minute only. Okay, I think it's done. By far, so the bottom line is that absolutely, the same signal in the same qualitative and to some extent quantitative trend is observed. Plotted here is Gini of the stars only in the Z band, UV light. We also did the K band. We didn't have the H band. Just a second. I forgot. For the K band, the star is a good proxy. And it goes exactly in the same trend. This is for star-forming galaxies down here. This is for quiescent galaxies, okay? And if you actually calculate the Gini coefficient of the dark matter itself using the Petrosian radius from the stars, the trend is observed also in the halos, in the dark matter distribution. Now, I'm not going to talk about M20, but you can also do another thing. You can you can rerun illustrious TNG 100 without baryons and see whether it happens. Now, there you have a problem. You don't have the Petrosian radius. So here we retain the fraction, the 10% innermost part of the dark matter halos. Otherwise, we don't know how to do the measure. It's not observed anymore. The trend goes away. So it's obviously an effect of the baryons on the dark matter halos. Now, so if time variations of Gini are variations of the gravitational energy, and through the virial theorem of kinetic energy, which scale of energy are we talking about? So simply the variations of Gini, okay, this one, if you transform it into a energy scale, it's of this order. It's about 10 to the 59 erg for the observed period of Gini. If you want a luminosity divided by the number of seconds in the observed delta Z. I'm telling you, it's about 10 to the 43 ergs per second. And I'm listing here a calculation made by Jonathan Nabb and Ostreicher a few years back, where they calculated the amount of gravitational energy due to the gas accretion onto the galaxies to form its stars. It's bigger. It's of the order of 10 to the 60. But together, actually just shy of 10 to the 60. Together, there you go. The total energy is about 10 to the 60, which is similar to the output by supernovae, and as we will discuss very likely in the discussion session that follows my talk, similar to the AGN. I throw this cartoon here, and I will simply comment that this follows from the measured bolometric luminosity of AGN, infrared selected AGN, and star formation. We published this several years back. Emanuele Daddi is the first author. And also by the reconstruction of the rate of accretion of stellar masses and supermassive black hole mass, which essentially go hand by hand. The AGN fluctuates a lot more and sometimes has big lumps and then steady and then catches up. But overall, the two are together. If you combine these results with these results, the conclusion is that the total amount of energy that you dump into the galaxy of the two components is similar. But and this means that I shouldn't be looking for the AGN as necessarily the source of quenching. But probably we will continue this during the discussion, and I better stop here. Thank you.
Okay, we have time for one question, and then we'll start the discussion.
Well, this relies basically on your ability. So the measure, if you think color gradients across the galaxy that change, this gets lost in the average, essentially. So basically, it relies on your pixel-to-pixel conversion from light into mass, which is probably better for the quiescent galaxy than it is for the non-quiescent galaxies, given all the. But yeah, that is, from the observational point of view, it could be a limiting factor. So this has to be done carefully. Yeah.
Okay, let's thank Mauro again.